Welcome to Winter Session Astronomy. I've made these PowerPoints with the hopes that they will add to what you learn in reading. I hope that you find them helpful. This is the material for the first day of reading in our class. There are some main points that I hope that you get from this material. The first is, I'd like you to figure out or understand where our place in the universe is. We all know that we live on a planet named Earth. We know that Earth orbits around the Sun and that it's part of a solar system. You're probably also aware that it's in the galaxy called the Milky Way. But where are we in the Milky Way? Where is the Milky Way? How does it compare to everything else in the universe? We're going to take a quick look at that today. We're also going to see that when we talk about astronomy, things are very large and very far apart. I want you to begin to appreciate that fact. While we're doing that, we're going to have to learn some new units of measurement, units that we use for distance. We're used to measuring distances in maybe feet, meters, miles, things like that. But we're going to find that we need to use some very different units of measurement to deal with the large distances that we encounter in astronomy. The speed of light is important in astronomy because, well, for one, we're studying light coming from objects, and we also use it to measure another distance, which is called a light year. We'll be able to use this and our very basic knowledge of rate times time equals distance to figure out how long it takes light to travel between objects. Finally, we want to take a look to help us understand how the science of astronomy is affected by the scale of size, distance, and time that astronomers are studying. So where are we? We're on Earth. Earth is located 1 astronomical unit away from the Sun. Neptune, the outermost planet, is about 30 astronomical units from the Sun, while Pluto, which we will learn is not actually considered a planet anymore, is about 50 astronomical units away. The astronomical unit has been defined as the average distance between the Earth and the Sun. It's 93 million miles. If we write that in scientific notation, it turns out to be 9.3 times 10 to the 7th miles. In science, we often use the metric system, and so an astronomical unit measured in meters, or kilometers, is 150 million kilometers. Again, in scientific notation, this is written as 1.5 times 10 to the 8th. Our solar system, of which Earth is a part of, is located in the Milky Way galaxy. Here's a picture of the Milky Way galaxy. Notice that it has a spiral appearance. We actually find out that the Milky Way galaxy is called a spiral galaxy because of its appearance. Here's a picture of the Milky Way when viewed from the side. It has a disc-like appearance in that it's very large from side to side in this measurement, but from top to bottom it's relatively thin. Notice also the distances on this picture are using a different unit of measurement. Astronomical units, or AUs, are very useful when we're measuring distances within our solar system. But when we move outside of our solar system, even to the very closest star, the distance is so large that we would have to measure very, very many astronomical units to measure that distance. So we use a larger unit of measurement. This unit of measurement is a light year. We'll talk about how big a light year is in a moment. But notice that the Milky Way from one end to the other is over 100,000 light years across. And the Sun is 28,000 light years away from the center of the Milky Way. Also notice that from top to bottom, the Milky Way is only 1,000 light years in dimension. Here's a picture of the Milky Way again from the top. This is showing the orbit of the Sun around the center of the Milky Way. We usually think of the Sun as being stationary, but it isn't. It actually is orbiting around the center of the Milky Way galaxy along with all the other billions of stars that make up this galaxy. Remember that it's 28,000 light years away from the very center, and so as such has a very large orbit that takes a very long time to complete. Here we see it takes 230 million years for the Sun to orbit around the center of the Milky Way once. So what is a light year? It isn't a unit of time, it's a unit of distance. It's the distance that light travels in 1 year. Light travels at a speed of 300,000 kilometers per second. Yes, that's very fast, and it's actually believed to be the upper limit of how fast anything can travel in our universe. If we wanted to figure out how far a light year is, we would use a very simple approach. If I told you that I was traveling in my car at a speed of 50 miles per hour, and I was doing that for 4 hours, you would know immediately how far I would travel. You would say, that's easy, it's 200 miles. I took 50 times 4, and I got 200. Well, we're going to use the same approach here, but just different numbers. The speed of light is 300,000 kilometers per second, and then we want to multiply by the amount of time. Well, it's a year, but we don't want to just multiply by 1. We want to use the number of seconds in a year, because our unit of time, our unit of speed is in kilometers per second, so this amount of time needs to be expressed in seconds. That would be the number of seconds in 1 year. If we do the multiplication, this turns out to be 9.46 times 10 to the 12 kilometers. Yep, it's a really big number. It's kind of hard to really take in what that really means. Here are just some comparisons or some things I used to try to put it in perspective. That distance of a light year would be 200 million times around the Earth, or 60,000 times the distance between the Earth and the Sun. That means that 1 light year is 60,000 times larger than 1 astronomical unit. Light travels so fast that in the time it takes you to snap your fingers, it can travel around the world. So, now we're talking about doing some calculations using the speed of light. You're going to do some similar calculations in your first virtual astronomy exercise that is also being assigned on the first day. For instance, what if we want to know what the distance is that's represented by the term light minute? We would use a very similar approach to what we just did for light year. We would be using the fact that rate times time equals distance. For light, the rate is the speed of light. Now, to find the distance for a light minute, we would multiply that speed times a minute, but we have to express that in seconds. It would be 60 seconds in 1 minute. We take 60 seconds times 300,000 kilometers per second, and our result is 18 million kilometers. A light minute is 18 million kilometers. So, how long does it take light to travel from the Sun to the Earth? This is another calculation that we can do. We start off with our expression, rate times time equals distance, but we're going to rearrange it to solve for time. We see that the time then is equal to the distance divided by the rate, or the speed. The distance we're interested in is the distance from the Sun to the Earth, divided by the speed of light. Well, we might say the distance from the Sun to the Earth is 1 astronomical unit, but because we're measuring our speed in kilometers per second, we really need to express the astronomical unit in kilometers, which is 150 million kilometers. If we then divide by the speed of light, we get 500 seconds, which turns out to be just a little bit more than 8 1/3 minutes. So, it turns out that it takes about 8 minutes for light to travel from the Sun to the Earth. Think about what that means. It means that when you're looking at the Sun, you aren't actually seeing the way the Sun is presently, but you're seeing the way that it looked 8 minutes ago. So, we talked about how we and our solar system are in the Milky Way. It turns out the Milky Way is one of about 30 galaxies in what we call the local group of galaxies. The local group is found on the outskirts of a local supercluster. and there are many superclusters that make up the universe. So, what are the limitations that an astronomer has to deal with as he studies what he's studying? One of them is timescales. It takes a very long time for anything to happen in astronomy. Take into account our own solar system. Our solar system is about 4.5 billion years old, and it probably took millions, if not billions, of years to form. When a star is forming, it can take hundreds of thousands or up to millions of years from the time that it begins forming until it's considered a full-fledged star. So as you can see, the timescales that we're studying are much longer than any lifespan of an astronomer. So that makes that's a difficulty that astronomers have to tackle. Also, astronomers are dealing with things that are very large. You cannot bring a solar system into a lab, a planet, a star. All of these things are very, very large. So how do these limitations affect the normal scientific approach? We might think of the scientific approach in a very rudimentary way that we learned probably in middle school science, if not before. You make a hypothesis, you perform an experiment to test your hypothesis, and then you collect your results. Well, it's performing the experiment that can be difficult for an astronomer. There are ways around this. For instance, instead of watching a star go through its formation process, an astronomer might actually be able to watch stars at several different points in their formation stages and sort of understand what the stages are for a star to form instead of watching a single one form. That's actually possible. He can also come up with models, things that models are based on observations that he has made, and then he's come up with a theory, well, not a theory, but a hypothesis about how that thing might have happened, maybe how might a galaxy have formed. Sometimes these models can be tested using computer simulations. So there are ways around the limitations that we see astronomers deal with, and it actually does still allow him to take a very scientific approach. As we go through the class, we'll learn more about this as we study different aspects of astronomy. There is another interesting effect of distance in astronomy, and I kind of alluded to it previously. In this picture, we see a telescope looking at galaxies different distances away. Keep in mind, those distances also refer to how long it took the light to travel to them. So, in this galaxy, it's 7 billion light years away. So that means it took light 7 billion light years to get here. So we're actually able to see into the past. Astronomers can look back in time by looking into the sky. Well, that concludes today's topics. I hope that you find this helpful. Remember that you can always contact me via email if you're having any difficulty with the class. I hope you're enjoying this class. I know it's going to be a lot of work, but I'm sure that you'll find it rewarding.